Okay, so this video is being made to answer some questions for one of my students that I'm tutoring. Also, it's just a general uh, treatment of how to use technology to solve binomial distribution problems. So what I've done is I put on this whiteboard a scenario that was presented to me from a college textbook about a roulette wheel. I'm simplifying things just a bit, but I mean, it will capture everything that was needed for that problem. And here was the question, or here was the statement, that in the simplified version of roulette, there was only one way to win. There was only one space on the roulette wheel that had 36 different spaces, all equally likely. So your chances of winning on a single spin were 1 out of 36. Furthermore, the question was, suppose that either 100 different people were going to play, or one person was going to play 100 times. You could think of it either way. And each time they played, the probability stayed the same, and you could either win or you could lose. Uh, the description that was given of the problem was one that satisfied all the constraints for a binomial probability distribution. That being that each trial, each of the 100 trials in this case, could be classified as success or failure, that the trials were independent. In other words, the outcome of one trial had no bearing on the outcome of any other, that we knew a fixed number of trials in advance, in this case 100, and that the probability of success on each trial remained the same. So sometimes students get confused about the difference between the trials being independent and the probability staying the same on each uh, trial. The reason that those things need to be separated is the example I always think of is somebody shooting baskets. Okay, well, let's just say that this is someone with no short-term memory. In other words, like if they make or miss a basket, it has no bearing mentally or anything like that about whether they make the next basket. So the trials would be independent if the statement that I just made were true. But if this shooter was not shooting from the same distance from the basket, from the exact same spot each time, then the probability of success on each shot would be different. In other words, if you took a shot from the free throw line compared to a shot from the 3-point line, those probabilities would not be the same. Okay, so anyway, in this particular roulette example, all of the criteria for a binomial probability distribution are satisfied. And so what I'm going to do is I'm going to go through and show you a bunch of different calculations that, some of them are just basic, some of them give students a little bit of trouble. So the first one that I have on here is, what is the probability that the player wins exactly 3 times out of the 100 times they play, or that 3 out of the 100 different people playing win? And so in that case, if I'm calling X, if the discrete random variable X counts the number of successes, I'm saying that that's equal to 3. Now, another thing, just as an aside, the discrete random variable for a binomial distribution can vary anything from 0, in other words, no successes, all the way up to n successes. So in theory, there'd be 101 different outcomes in this particular case. The roulette player could win no games all the way up to, as unlikely as it is, 100. They could win 100 times in a row. Okay, so we're finding the probability first that X is exactly equal to 3 using technology. And by technology, I mean a TI-84, or in this case, I'm going to be using what's called I believe it's called the Calc 84. It's an online tool. I've made some videos on YouTube about it. So on that, for a single probability, a single binomial probability, we use binomial PDF. And the inputs on that, for this version of the calculator, it doesn't specifically it doesn't say, hey, tell me what N is, tell me what P is, tell me what X is. So I need to know the syntax. And so when I fill it in, I'll give the first number as 100, and then I'll put in a comma. I won't write n equals 100. I'll just put 100. I'm just specifying it here so that you can clearly see what I'm doing. I will tell the calculator that the probability of success on a given trial is 1 divided by 36, and I will let the calculator do that division for me. And then I will tell it that I want it to find the probability of exactly 3 successes, and then it will give me an answer. Okay, so let me switch over to the calculator, which I guess I don't have open yet. There we go. Well, maybe. There we go. Okay, so on the TI-84, Calc-84, or whatever, to get to the binomial probability distribution, you go second, vars. And so you'll need to scroll down to find binomial. Now notice there's two, and we're going to use both of these today, so you'll see how to use both binomial PDF and binomial CDF. But for a single probability, as in if you write it out, it's the probability that x equals whatever, then it's PDF. Okay, so I'm going to choose that. Now again, if you're using a newer version of an 84 or an 83 or whatever, it may look a little different. It may, as soon as you hit binomial PDF, it might say n equals, and then you just fill it in, and it might say p equals, and then you fill it in, etc. On this version, I need to fill in the values according to the syntax, so 100, comma, and then the next thing is the probability. So if I were to do 1 divided by 36 and separately and round it and all that kind of stuff, I'd lose a little bit of accuracy, so I can just do that. And then we're doing 3. And then, I don't know, it's just habit for me. I always close the parentheses, enter. And so the probability there is approximately 0.225. Okay. So for the next one, I want to find the probability that x is, I'll say it this way, no more than 3. So it could be that you win 0 times, or you win once, or you win twice, or you win 3 times, up to 3, up to and including 3. So this is a binomial CDF scenario. So C stands for cumulative. And this time I'm not going to write all the different descriptors out. I'm just going to write 100. So it's the same syntax. So when you do binomial CDF, you put in the number of trials, in this case 100, the probability. And when you put in the x value, you're putting in the value that you're counting up to. It will include 3. So this will be, if I were writing it out, all the individual probabilities, it would be the probability of x equals 0, plus the probability that x equals 1, plus the probability x equals 2, plus the probability x equals 3. So this time, second vars, binomial CDF, and you'll see how much of a difference there is between PDF and CDF. So approximately 0.698. 0.698. So there's approximately a 70% chance that if you play 100 times, you're going to win 3 times or fewer. Okay, so now I just wanted to sort of compare that to, and maybe this seems obvious to you. If we just say instead that the probability that x is less than 3, then this time we don't want to find the probability, we don't want to go up to 3. In this case, since it's a discrete random variable, we're only going to go up to 2. So in other words, this would be the same as the probability that x is less than or equal to 2. And so it'll be exactly the same setup as above. It'll be binomial CDF, But this time, instead of going up to 3, we'll only go up to 2. So it'll be 100, 136th, and 2 instead of 3, because we're not including 3 in this case. All right, so let's see how much. Well, we kind of know actually what that's going to be. Don't even really need to do the calculation, because we already know what the probability is that x equals 3. We got that right here. So if I were to subtract that off, I'm going to just go ahead and do that real quick in my head. Then I'll go do it on the calculator just to show you. But we'd get something like, what, 0.473? So it should be approximately 0.473. And that, again, I got just by taking up to 3 minus the value that we won't be including this time, exactly 3. And so I think 0.473 is the answer that we'll get, unless I'm subtracting wrong in my head. Okay, so second, vars, binomial CDF. Oops. Okay, so let's do that. I don't care about that right now. Second, vars, binomial CDF 100. Oops. 100. 1 divided by 36. And 2 this time. So as you can see there, 0.472 is indeed the answer that is produced. All right. Now, what's the probability that x is greater than 3? Sorry. So I'm going to spend a little bit more time explaining this. Using technology, and I don't know, there might be some online calculators out there somewhere that will count up, but the TI-84 or the Calc 84 like I'm using, they don't do that. They count down. So in other words, if I want to find the probability that x is greater than 3, I'm faced with a couple of different scenarios. I could individually calculate the probability that x is 4 and 5 and 6, all the way up to 36, and add all those together. Tremendously time consuming. Not going to do that. Or I can utilize the idea of the complement for probability and say, okay, well, if I want to find the probability that x is greater than 3, in other words, 4 or higher, what I could actually do is take 1 minus the probability that x is less than or equal to 3. So the reason that works is because 1 you can think of as the probability that any event will happen. In other words, that I'll either have 0 wins or 1 win or 2, all the way up to 36. And to find the probability that x is greater than 3, I want to subtract off all of the events except for the ones that I'm interested in. The ones that I'm interested in are the ones bigger than 3, so I want to subtract all of the events that are not bigger than 3. In other words, that are less than or equal to 3. So for this problem, what I would do is, if I hadn't done any of what I've done above, I would do 1 minus the binomial CDF. I would do 1 minus this binomial CDF right here. So in other words, the calculator actually would do 1 minus 0.698, which, again, I'm doing this in my head. So if you're watching this and you're like, oh, he's off on his subtraction, that's possible. But I believe that if you did 1 minus 0.698, you would get, what, 0.302? You know what? I should double check myself. I'm making this video in the morning before I've done any math whatsoever, so you never know. 1 minus 0.698. What do you know? 0.302. I was right. Okay, now again, so now the probability that x is greater than or equal to 3. So that's sort of the idea that's similar to when I was talking about the difference between these two. With a discrete probability distribution, you have to be careful. Okay, so what I'm getting at here is that if you're finding the probability that x is greater than or equal to 3, then in that case, what you're doing is you're subtracting off everything that's less than 3. In other words, you want to do 1 minus the probability that x is less than or equal to 2. So again, if I hadn't done any of this stuff up above, I've already done the probability that x is less than or equal to 2. I know that's 0.472. So 1 minus 0.472, I'm going to say is 0.528. So those are the basics of how binomial probabilities can be calculated using technology. And so just take your time, think through exactly what the question is asking you for. Make sure that when you think of it, even if you don't write it out, that you are at least thinking carefully about whether or not we're doing, for example, less than or equal to versus less than, or greater than versus greater than or equal to, and then make sure that what you get into your calculator reflects the true situation. And then, of course, also, when you're doing a problem in a binomial probability section, it's easy to just start flowing with the idea that, oh, everything's binomial probability, just like we tend to do with normal distributions. Not everything's binomial. So think through scenarios and make sure that they fit the criteria for a binomial distribution. A handy acronym that comes from, well, it's probably not just from AP, but it's where I learned it when I was teaching AP statistics, was BENS. And so that acronym for deciding whether or not you have a binomial distribution is, can each trial be classified in a binary way as a success or a failure? Are the trials independent? That's the I. In other words, does one trial have any impact on another trial? N, is the number of trials fixed in advance? In this case, for example, we thought of the number of trials as 100. And then S stands for the same probability on each trial. And that's what I was talking about at the beginning of this little video, that like with the person shooting baskets, if they're not shooting from the same place all the time, even if they don't remember what happened before, the probability of success on each shot does not stay the same. Okay, so I hope that helps. And it's a fairly easy process using technology. There's also tables. There's also a formulaic way to do these things, and all of those things are fine. But this is how you do it using technology.